Okay. Well, thank you. Thanks again for the introduction, and thanks for the invitation. I'm delighted to be here talking to you guys. I would be more delighted if this was actually held in person. I love Porto. I would have loved the excuse to go there. Sadly, that's not to be. But let me anyway applaud the committee for organizing this against what must have been difficult odds, and everyone who's attending for trying to better oneself by participating in this event and making it a success. So again, nice to meet you, everybody, and I hope I won't be wasting too much of your time with my lecture, which is slightly ambitious in terms of its scope, and may not actually, I won't be able to do justice to all of these things that are alluded to in the title, but I'm hoping that I will be able to communicate at least some of the excitement about plasma physics in several of its sort of manifestations that I'm more familiar with. Cool. So if you wish to ask questions throughout the lecture, that's fine. I won't be actively monitoring the chat because I'll be, focused on the talk. But if something shows up, maybe the organizers can interrupt me and we'll clarify it as we go along. Cool. So I suppose, maybe I thought a good place to start is by giving everybody a more specific idea of what a plasma is and the sorts of complexities that arise when you're trying to study plasma physics. So here's what the plasma is. So plasma equals this person plus that person. I'm hoping that that you will recognize these two faces. So that's Maxwell and that's Boltzmann. And the reason I say this is that plasmas are a collection of interacting charged particles, many of them, and they interact via their mutual potential. And so to explain the interaction of this hot electron and ion gas, for example, you typically, you will need Maxwell's equations. And of course, because there's just so many of them, you're better off using a statistical description as provided by Boltzmann. Now, more recently, these two gentlemen also feature in plasmas that we are interested in, even though I won't talk very much about this. This person is Einstein, of course, and he is here because in many astrophysical applications, special relativity effects in plasmas are important, and oftentimes general relativity effects, such as, for example, if you're studying accretion around black holes, or if you're studying neutron star collisions, these are all plasmas, and there you can't neglect relativistic effects. And in even more exotic cases, such as magnetars and pulsars, QED effects become important. And so Julian Schringer is here to do to show that that's also possible. Now, it probably won't surprise you that the combination of the theories worked on by these four people on your screen right now leads to something that's pretty complex. And if that's your intuition, you are correct. So plasma dynamics is indeed very complex and perhaps best described as out of equilibrium statistical electrodynamics, sometimes with relativistic effects and sometimes with QED effects. Now, plasmas do amazing things, and we study them both because they do amazing things and we are intellectually curious. And so, as physicists, sometimes we're driven by the question itself and not necessarily its practical applications, but also because there are many practical applications of plasma science. So what you're looking at here is actually an example of both. This is the sun flaring. So you probably have seen images of solar flares before. What you're looking at is, so all of these contours here, I hope you can see my screen. These are actually, so this is actually radiation that you're seeing from the plasma in the solar corona. And the plasma is very strongly anchored to the magnetic fields on the surface of the sun. So it actually traces magnetic field lines. So these loops are loops of magnetic field. And because the photosphere, so the surface, if you will, of the sun is turbulent, these magnetic field loops are being continuously twisted by random foot point motion. And sometimes that leads to a lot of tension being applied to these magnetic fields, and their relaxation can lead to these explosive events, such as solar flares. So that's, of course, a fascinating thing to try to understand, how exactly does this happen? But if you're more engineering minded or more practical minded, these sorts of events launch highly energetic electrons that, in extreme cases can actually fry satellites. And, that's a problem for communications on Earth, et cetera, et cetera. So it launches a discipline known as space weather, which tries to understand the Sun-Earth connection and what's going on there. And that, of course, at the heart of that is nonlinear plasma dynamics, such as you're seeing here. So let's talk a little bit about why plasma physics matters. So I said this already. It's interesting per se as an intellectual frontier of theoretical physics. Sorry, and sort of, by the way, the question that often arises is this. I sometimes explain to colleagues that a lot of plasma physics is pre-relativistic and pre-quantum. And they sort of stare at me in disbelief and think, how can that be any interesting? And well, it's interesting in the sense that out of equilibrium statistical electrodynamics is not a solved field by any means. And so that alone, so Maxwell plus Boltzmann, leads to enormous complexity. And that's quite enough to keep a lot of us busy. So I'm not overstating it when I say that it's an open intellectual frontier of theoretical physics. But in terms of sort of scientific and engineering questions, you may have heard of fusion as an alternative clean energy source, so much so that the National Academy of Engineering here in the US has chosen fusion as one of the grand challenges for engineering in the 21st century. And I'll talk more about this. Fusion at its heart, whether it is successful or not, depends on how much we can control the plasma and predict and understand its nonlinear dynamics. So that's quite a challenge. And then there's a lot of applications in astrophysics. And one of the ones that I will talk about a little bit is the origin of magnetic fields that pervade the universe. And that ties into the magnetogenesis problem and the Dynamo problem, meaning the amplification of magnetic fields via plasma motions. Things I won't talk about so much are origin of cosmic rays, which are thought to be accelerated by plasma processes throughout the universe, black hole emission and jets, and a lot of other things like neutron star collisions, magnetars, etc. Many astrophysical environments are essentially plasmas that we try to understand, and that depend on, so our understanding of those environments depends on a clear understanding of plasma phenomena. And then people, of course, explore applications of plasma physics to things like tabletop particle accelerators achieved via, very powerful lasers, space weather that I've mentioned already. And then there's a whole industry surrounding low temperature plasma physics with a lot of, real industrial applications, but I'll say nothing about that because that's not my domain, and nor do I have the time to explore it here. Okay, so here's a very brief introduction to plasma physics. So 101, as they would call it in the US's denomination for introductory courses. So, let me say, I say to you, a plasma is a collection of a large number of charged particles, and they're interacting, for simplicity, via their own Coulomb potential, right? So I have a particle here, they are at a certain distance. We can compute the force between those two particles, and how do I solve the evolution of this system? You might say, well, that's very simple. I'll solve F equals ma for each particle. Trivial. Okay. So what do? I choose a particle. I compute the force on that particle due to every other particle in my system, and that gives me the acceleration. I'll move it forward, and I do this for every particle. So that's called an n-body problem, and you can do that if you have 2 or 3 particles. Computationally, you can do it if you have a few million particles, but there's many more particles than that in a plasma. There's in fact, billions and billions, right? And so this is not going to be a fruitful approach, because even though it is sort of the most rigorous approach, you're not going to be able to solve anything, right? That's nor analytically, nor really computationally. And this illustration here is actually a simulation done by a high school student that was interning in my group. And this is just to show you the sort of complexity of electron trajectories that you can get in a plasma if you have a magnetic field that you impose that's varying sinusoidally as a function of time. Okay, so this picture here is, imagine that you give these electrons a magnetic field that you prescribe. This magnetic field varies as a function of time at some frequency, and you ask, what are going to be the trajectories of these electrons? And this is what you get. You see the electrons with random velocities initially, and you get this sort of behavior. As an illustration, I think it makes it quite clear that even sort of prescribed simple magnetic fields give rise to a lot of complexity. And magnetic fields in a plasma, when they are evolved self-consistently, easily become turbulent, right? And so it's basically hopeless to think that you're going to be computing trajectories exactly for anything that approaches realistic conditions. Okay. So we don't do this, right? Because if you were trying to do this problem with an n-body simulation, you'd basically be stuck. You wouldn't be able to solve anything. So instead, like I said, we often adopt sort of a more statistical description. And here's Boltzmann equation, if you wish, where the acceleration is given by the Lorentz force, electric field plus a magnetic field acting on particles that are at position r with velocity v. Okay. So how do you solve this self-consistently? Well, you do it as follows. You say, I'm going to solve this equation, but I need electric fields and magnetic fields. Wonderful. So I know Maxwell's equations. Here they are. And by the way, they are written here in CGS units because we are strong believers in the fact that the electric field and magnetic field should have the same units. So we use CGS tendentially. So there you are. So that's it. So that's Maxwell. And then you say, well, but Maxwell depends on charge density and depends on current density. So how can I compute those? Well, you do that because charge density is the sum over all species of density times charge. And the density is just the integral over velocity space of the distribution function. And the velocity is the first moment. So this is a closed system, and it's a beautiful thing in a way, right? So you solve this equation to get F, you compute the current, and you compute the density, and the charge density, and the velocities. You plug that into Maxwell's equations. You compute the consistent electric fields and magnetic fields. You plug the whole thing back, and you solve again, and you iterate until you converge. Now, this is simple to state. Here's a simulation. What you're looking at is just one-dimensional in position and one-dimensional in velocity, and you're looking at contours of F. And there's some instability that doesn't matter here. again, looks quite complicated, but just to demonstrate that we can do this simulation, and you're now evolving f as a continuous object, right, the distribution function, rather than thinking of individual particles, which is sort of a more challenging problem. Now, of course, this is a fully nonlinear system because to compute f, I need electric and magnetic fields, but to compute the electric and magnetic fields, I need to know f, right? So it's fully nonlinear, and f itself is a 6D object plus time, and that's incredibly unpleasant. Of course, you are not going to make a lot of progress trying to solve this analytically. It is sort of very difficult. It took someone like Landau himself to solve the linear version of this problem and therefore derive what is known as Landau damping in plasmas. And it took a Fields medalist, Cédric Villani, recently, a mathematician, to show some interesting effects about the long-term behavior of the solutions to these equations. So, I'm not just name dropping, I'm saying this so to highlight the challenge in solving this equation analytically, or deriving a lot of insight from an equation like this. Now, you can take the extreme opposite view. You can say, maybe I can think of this plasma as a fluid of electrons and ions interacting with each other, but I don't need to think about these particles. Maybe they're colliding enough, right? They collide all the time, and therefore they have a fluid-like character. The flow of this object, this plasma, is like water, except of course it now responds to the Lorentz force. And so if you adopt that, so assuming that there's enough collisions, the distribution function is approximately Maxwellian, you'd write equations like this, where rho is mass density, so this thing is like a continuity equation. This thing here is actually just F equals ma, right? So this is the momentum equation, where the forces acting on your fluid are pressure gradient, viscosity, Lorentz force. This is the acceleration. And then you need a diabatic equation of states, an equation for pressure. Again, you need to know the magnetic field, so you couple that with what's left of Maxwell's equations. And these are called the magnetohydrodynamic equations. They're hydrodynamics, but now there's a magnetic field, so you refer to this as magnetohydrodynamics. And the first person to actually, sorry, excuse me, I've been lecturing online for over a year now, and it's still difficult to get things right. Okay, so this is Alfvén, who was the person to coin this term, magnetohydrodynamics, and to first use these equations to derive a type of waves that is characteristic of plasma called Alfvén waves, disturbances in the magnetic field that propagate along the magnetic field. And for that work, he got the Nobel Prize in 1970. So just to summarize, these are two extreme views of the plasma. You either say, I'm going to solve Boltzmann equation for the distribution function. You do that if collisions are infrequent. Or you say, I'm going to solve the magnetohydrodynamic equations, and you do that if collisions are frequent enough. Now, unless you're a genius, it's very hard to get intuition from just staring at the Vlasov equation, the Boltzmann equation. But equations like this appeal very much to our intuition, because everybody has an idea of what a density is, or what the pressure is, or what the flow is, right, of water. I have a plasma flowing, I measure velocity at some position, I understand that concept, right? So oftentimes we try to work with these equations if we can, if for no other reason, just the fact that these are talking about quantities that you can measure and that you have a lot of intuition about. And also, oftentimes, well, not oftentimes, always, it's much easier to solve these equations on a computer than it is to solve Boltzmann, because of course, all of these quantities here, density, velocity, etc., these are quantities that are just three-dimensional, the x, y, z, whereas f was a 6D object, right? So in terms of computational costs, it's much easier to deal with these equations than it is to deal with the Boltzmann equation. So here's an example of something that these equations are used for. This is a 3D simulation of an accretion disk around a massive central object, perhaps a black hole. The object itself is not simulated, right? But the accretion disk is. And you see that these equations capture turbulence in this accretion disk, and that turbulence is why matter in the accretion disk accretes much faster to the central object than it would if the only thing causing your break of angular momentum conservation was viscosity, because viscosity is extremely small in many of these accretion disks. Awesome. So now that I think I've set the stage, I'm sorry, I'm looking for a watch, excuse me, just to keep track of time. Now that I've set the stage, we can talk a little more about the things in the title, namely some aspects of fusion and some aspects of magnetic fields throughout the universe. So let me tell you a little bit about fusion. So the sun shines because fusion happens in the core of the sun, right? And we've been trying to do that on Earth for quite some time now. Our problem is, of course, that we don't have the kind of gravitational pull that the sun has, right? So you can't very well just come up with an experiment in the lab where you're going to confine a plasma gravitationally by just having, you know, some source of gravity there, right? So we're trying to do it with magnetic fields instead. And it all relies on taking some gas, right, and heating it up so that two nuclei can overcome their mutual repulsion, overcome the Coulomb barrier, and fuse. And, you know, in this particular case, for example, deuterium plus tritium, you get out an alpha particle, so helium plus a neutron. And the reason this reaction, this fusion reaction in particular, is the one that we most often consider has to do with cross-section, the shape of the cross-section as a function of energy. And, you know, if you think that it's difficult to heat something to very high temperatures, what you seek is the reaction that's going to maximize cross-section at the smallest possible temperature, right? So you could be doing it with helium-3, or you could be doing it with deuterium, but the reaction that has the highest cross-section at the lowest temperature happens to be deuterium tritium. And so that's why we sort of do it. And the whole idea is very, very simple. You know, this reaction produces an alpha particle with 3.5 MeV energy. It produces a neutron with 14 MeV energy. The neutron, of course, doesn't respond to electric fields or magnetic fields. So it comes out and you use it presumably to activate some sort of heat cycle. And the helium stays confined, and you hope to use the energy from the helium to keep your plasma hot. So a self-sustaining reaction. This is not easy to do. So ask yourself, how do I confine a gas of electrons and ions? So you try to put it in some container. Let's say it's some sort of cylinder. And of course, you know, if you these random is in random direction, right? So they'll everywhere and eventually hit the walls of your device and recombine there, and you're out of plasma. So one way to do it is just say, well, let me have a magnetic field threading this cylinder. And I know that if I do that, the particles can move freely along the magnetic field, but perpendicular to the magnetic field, they have to go in Larmor gyrations. And so they're confined, at least perpendicular to the magnetic field. If I want them also to be confined along the magnetic field, all I have to do is turn this cylinder into a donut, right? Torus. And that's the whole idea behind sort of the most advanced schemes in magnetic confinement fusion. And we call this a tokamak. Here's the most recent conception of one in a model that MIT is proposing here called Spark. You're seeing a cross section, of course. This thing is a toroidal chamber that's been cut here in the drawing so that you can see the glow of the plasma inside. This is just a cartoon, of course. This is not a real experiment. We're building it now hoping to have it working in 2025. Okay, so the gas is here, you heat it up, fusion reactions happen here, neutrons escape, and you get energy. It's a beautiful thing if we can make it work. But this is not easy. And one of the reasons it isn't easy is very easy to understand. Okay, so let me go back to this cross section here, and let me call your attention to this number, 100 keV. 100 keV is around 100 million degrees centigrade. So that's hotter than the surface of the sun. Okay, the sun doesn't have to worry about this, but we do because we want to maximize fusion reactions. And so we want to operate at very high temperatures. And so that means that on this drawing, there's going to be a plasma here, which at its center is sort of at, maybe 20 keV, okay? So 100 million degrees Celsius. But over here, well, there's going to be a material surface here, right? And materials are going to be at room temperature. So the temperature gradient from here to here is probably the largest temperature gradient in the entire solar system. Okay? It goes from 100 million degrees Celsius to basically, 30 Celsius. Okay? And this distance, this is a person. So this distance is about 1 meter, if that. Now, as physics students, you probably know that there's one thing that nature does not like, and that's gradients. Nature doesn't like density gradients, Rayleigh-Taylor instability. Nature doesn't like velocity gradients, Kelvin-Helmholtz instability. Nature doesn't like temperature gradients. Okay, and so when you set up a temperature gradient that's as large as this, things go wrong, right? And one of the things is that the plasma decides that it doesn't want to have that temperature gradient and sets up all sorts of instabilities that lead to turbulence. And so what you're looking at here is a simulation done by my colleague Nathan Howard, maybe 6 years ago now, of what that turbulence might look like as shown by contours of electrostatic potential. And this is multi-scale turbulence because it has components that are due to the ions and components that are due to the electrons. And the electron to ion mass ratio is about 2000, and square root of that is around 40, right? So the Lama radius of an ion is basically this big. The Lama radius of an electron is this big. And these two turbulences happening at different scales talk to each other and inform each other. And you can see it here. You see, so these big blobs that you see are turbulence on the ion scales. But there's fine striations on top of each one of these blobs, and that's turbulence at the electron scales. And the fact that these two turbulences talk to each other means that if you want to get this right, you have to simulate all of these scales simultaneously. So to give you an example, for those of you who are interested in computational details, this simulation, this one simulation, the cost of it was 18 million CPU hours. So that means that if you have 18 million CPUs, you'd run them all in parallel for 1 hour to get this. Okay, that's not how it's done. This is run on tens of thousands of processors simultaneously. So parallel computing, right, state of the art then, and leads to this incredibly complex scenario that we then sort of mine for data and try to make better sense of. Now, it's not just turbulent tokamak plasmas that are turbulent. Space and astrophysical plasmas are almost invariably in a state of turbulence themselves, even if the reason for that turbulence tends to be different from just temperature gradients. And so this beautiful illustration that you can see in my virtual background is a simulation of turbulence done by my former student, Gianandrea in Cingolo, of turbulence in an accretion disk, simulated using sort of an equivalent of the Boltzmann description. So just to illustrate that complex turbulence like this abounds, you find it in fusion plasmas, you find it in astrophysical plasmas, And it's this turbulence that ends up setting the proper macroscopic properties of these media, right? So if I want to know how long it takes me to dissipate, to diffuse the temperature in this plasma, right? That diffusion is anomalous. It is set by the turbulence. It's not set by collisions of any means, okay? So that would be very, very small. The fact that this is turbulent means that your plasma is going to cool off much quicker than otherwise. Okay? Incidentally, when you put a drop of milk in your coffee, you stir it so that you mix it faster, right? You're creating turbulence because that leads to faster mixing. Similar thing here, right? If you didn't stir, it would take a long time for that one drop of milk to turn your black coffee into gray coffee, right? So if you stir it, if you give it turbulence, it's so much faster. So same thing in a fusion device. Sheldon, of course, understands turbulent transport perfectly. So I put this up as a bit of a joke, as sort of a for kicks, right? But it's actually quite interesting that they actually got a fusion expert to write what's on the board here. And so it's interesting to go through this. So what Sheldon is estimating here is the ion diffusion coefficient, basically how fast you lose temperature because of this turbulence. And he's talking about the temperature gradient. You see 1 over T the TDR, that's the normalized temperature gradient in a tokamak. And down here, it's explaining something that actually is correct. He's saying, well, I have these turbulent eddies, but if somehow I can break them up, maybe because there's a shear flow, they become smaller. And if they're smaller, then that means that my turbulence diffusion becomes smaller. So that's what Sheldon is explaining here. So I thought you might find that amusing. Now, turbulence isn't the only instability that fusion plasmas have to contend with. There are, so as it happens, turbulence is sort of benign because, okay, so you lose temperature and particles and energy faster than you expect, but it doesn't lead to any major disruption of your fusion device. But you can also get sort of the tokamak equivalent of solar flares. And these are like macroscopic disruptions. So here's a filament that's about to be expelled from the plasma, very much like the solar flare that you saw at the beginning. And that launches a lot of particles, very fast particles that can then hit the walls of the device and do things like this. So this blob here, that's, those tiles have been melted by extremely fast electrons that were produced by the plasma. So this you cannot have, right? Because eventually, 2 more of these, you will actually pierce a hole through the wall, right? And that's basically the end of your experiment. And so, there's this fascinating complexity and myriad modes of ways that things can go wrong, right? All these instabilities that we have to somehow master, both at sort of, if we can, at the theoretical level, but at least with simulations that set an operational space for fusion devices. Right? We know we can operate in some parts of that operational space, but not everywhere, because many of these, many values of parameters lead to instabilities that will then cause things like that, and that's unacceptable. Cool. So there isn't only the magnetic type of fusion, magnetic confinement. Another variety that I won't say very much about is inertial confinement fusion. This is a completely different concept. The idea here is that you have a pellet, maybe sort of a pellet is something that is sort of marble sized, and it contains deuterium and tritium, and you put it inside of some chamber, and then you use extremely powerful lasers to, if it's indirect drive, as they call it, these powerful lasers hit the walls of some confinement chamber, called the hole round. That creates X-rays, and then the pressure of those X-rays is supposed to make the target compress and generate enough pressure that you can fuse the contents. Okay. Now, does this work? Not yet. And it's easy to understand what might go wrong here. So here's a simulation, and okay, so think you have a balloon, and now you have fingers trying to compress that balloon, right? And you know that if you compress here, the balloon will expand elsewhere, right? So what you try to do is to have many fingers compressing that balloon as uniformly as possible. Okay? And that's hard, right? To achieve that degree of symmetry so that you result in uniform compression rather than compression here, expansion there. That's a very difficult thing to do. So what you're seeing here is basically instabilities that are driven inside of this capsule by virtue of the fact that the irradiation by these lasers isn't actually uniform. So this is very much research in progress, as is magnetic confinement fusion, and it leads to all sorts of interesting physics that go beyond just looking at the actual fusion itself. And here's one of the interesting aspects of these laser plasma interactions or laser target interactions. So many times what happens is when you shine a laser at a solid target, so in this case, the solid target would be sort of at the bottom of this blob here, of this green blob. So you shine the laser, you ionize the target, and you have an expanding cloud of material coming towards the laser. And then you have a temperature gradient, because if you're closer to the laser, you are hotter, right? And if you're further away, you're colder. But you also have a density gradient, because if you're closer to the surface, you are more dense. If you're further away, you're less dense. And as it happens, there's a battery mechanism that is generated by virtue of the fact that the temperature and the density gradients are not aligned. They can be perpendicular to each other. That's a battery that generates a magnetic field. And what you're seeing here is a simulation by Kevin Scheffler, who's a postdoc working with me some years ago, showing how when you set up that green blob, as it were, right, a blob of density with a temperature gradient that's perpendicular to the density gradient, you generate these magnetic fields like this. Okay, so that's called the Biermann battery effect. And people do this routinely in laser plasma experiments, but it is also thought that this same mechanism, the Biermann battery, is responsible for generating seed magnetic fields throughout the universe. Maybe because you have a supernova explosion that drives a shock front, and at the shock front, you can have density and temperature gradients that are misaligned and generate magnetic fields. So this is sort of the jumping slide where I go from talking about fusion to talking about magnetic fields in the universe. So we use magnetic fields on Earth here to confine plasmas, but elsewhere in the universe, magnetic fields are just there. And the only thing that seems to be as ubiquitous as plasmas in the universe are magnetized plasmas, right? So magnetic fields are found literally everywhere and at all scales. So of course, Earth has a magnetic field. This is a famous simulation of what that magnetic field might look like by Glatzmeyer 20 years ago. That magnetic field of the Earth interacts with magnetic field coming at us from the sun and generates a very complex magnetospheric structure that essentially protects us from very, very fast electrons, very energetic electrons coming at us from the sun, right? And generates what's called the magnetosphere. Very complex environment. The sun, of course, has its own magnetic fields. And then you start going to larger and larger scales. So here's a galaxy, this is M51. And this is supposed to be tracing the structure of the magnetic field in the spiral arms of that galaxy. And then you say, well, what about galaxy clusters? Are there magnetic fields at the scale of galaxy clusters? And the answer is yes, there is. You take galaxy clusters and you try to measure magnetic fields around them, and you find that this magnetic field exists and is organized at the scale of the clusters themselves. So this is fascinating. It reveals, sort of this ubiquity of the magnetic field in the universe prompts many questions. One of them is, where do they come from? Because, so I'm not an expert in string theory or anything like that, right? But the conventional wisdom these days is that magnetic fields themselves weren't really created at the Big Bang, right? So there has to be some sort of plasma-based mechanism by which you are going to create these magnetic fields, essentially from nothing. And the Biermann battery that I just talked about is one possibility. You generate some sort of seed magnetic fields. And then you ask what happens to them as the plasma sort of moves and evolves these magnetic fields. So let's talk a little bit about that. So all of these environments, the Earth's core, the sun, solar system, the interstellar medium, galaxies, galactic clusters, they're all plasmas. You can think of all of these environments as plasmas. And so if you could think of them as plasmas, you might want to write down an equation for how a plasma evolves a magnetic field. And so I showed you, I flashed this equation earlier. This is Ohm's law for a plasma. You might recognize it without this term. It just says electric field equals resistivity times current. When you were in kindergarten, you saw voltage equals resistance times current, right? So this is sort of the differential version of that. This electric field equals resistivity times current. But of course, the plasma is moving. So what you have to do is you have to write down the electric field in the frame moving with the plasma, which is electric field in the laboratory frame plus U cross P. You combine this equation with Faraday's law. So you take the curl of this, and curl of E is minus the PdT, so you get the induction equation. So this equation tells me how the magnetic field will evolve in a plasma subject to flows, plasma velocity U, plus resistive diffusion, okay? So without this term, this is nothing but the diffusion equation, like the heat equation. But this term is quite interesting, and it gives rise to non-trivial behavior of the plasma, of the magnetic field in a plasma, and in particular, can lead to amplification of that magnetic field. That's so-called the Dynamo Problem. One curiosity about this equation is that it's linear in magnetic field, in B. So if your magnetic field is initially 0, all you're ever going to get out of this equation is 0. So you need to provide some seed for these flows to operate on. And that seed may be coming from the Biermann battery, but there are other plasma-based processes that might also give a seed like that. Okay, let me ask the organizers, how long should I speak for? Do I have another 5 minutes, perhaps?
Yeah, 5 minutes is all right.
Okay, thank you. Good. So I'll be quick from here. I don't need to speak forever. Let me just present you with a very simple estimate. Let's assume you had a magnetic field present when Earth formed. Now you think that the outer core of the Earth is an MHD fluid, it's a plasma, okay? And we know what its properties are. So you know that based on the properties of that fluid, if you had a magnetic field present when Earth was formed, it would take about 10 to the 5 years for that field to ohmically diffuse. But we know from paleomagnetism, so essentially measures of the magnetic field on Earth, that the Earth has had basically a constant magnetic field for essentially however long it's existed, around 10 to the 9 years. So you conclude from this that the only possibility is if the Earth actively generates its own magnetic field. Right? So the motions of the core of the Earth are such that via the induction term, they continuously generate the magnetic field of the Earth so that this term cannot just dissipate it away. Okay? And that's sort of a demonstration of the need for a dynamo on Earth, but it's similar for the sun and similar for many other magnetized planets and stars. More recently, we're trying to go beyond this MHD description of dynamo and actually look at dynamo in collisionless plasmas. And that's very complicated. It's computationally very difficult and analytically also very difficult. My student Muni Zhu is working on this. This is the first simulation of a completely ab initio first principles dynamo. You can see that you sort of start with nothing and very small scale fluctuations arise. And then there's some sort of complicated dynamics. They start merging and creating larger scale magnetic fields and so on and so forth. So just to point out that this is very much ongoing research. The dynamo problem is far from solved, especially if you're looking at it in a collisionless plasma. Let me skip this. Plasma physics has recently met quantum computing, so there's this idea that quantum computing can offer exponential advances in speed-ups in computing power. Plasma physics requires vast computational resources, but it's fundamentally nonlinear, so it's not at all obvious that you can use quantum computing to solve plasma problems. This is something that I'm working on and happy to talk about it in more detail if you have questions. I'll skip this. These are two Portuguese physicists working here in the US, applying very sophisticated machine learning techniques to try to come up with more sophisticated models to simulate plasmas with and understand plasmas with. I'm also happy to answer questions about this. Let me just put up my summary slide and state that I hope to have convinced you that plasma physics is intellectually rich and broad in scope. There's many opportunities for deep theoretical contributions and for cutting edge computing. The success of fusion is critically dependent on understanding nonlinear plasma dynamics, as is the understanding of a wide range of astrophysical environments. And, supercomputing has been one of the pillars of plasma science, so there's theory, there's experiments, there's observations, but, over the last 20, 30 years with the dawn of advanced supercomputing, we've really made great progress. And maybe we're at the dawn of a new scale because exascale computers are coming up, machine learning, quantum computing. So stay tuned. I expect that the next decade is going to bring, quite significant advances in this area. So I'll stop here and thank you all for your attention, and I'm happy to entertain questions. Thank you.
Thank you for a very interesting talk. We have quite a few questions in the chat, so I'll give the word to the participants right away. So the first one is from Thibault. You should, let's see if this works right now. So you should be able to turn on your camera and microphone and ask a question.
Can you hear me?
Yeah.
My question was a bit simple, and it was on slide 6 when you present Maxwell equations. I was wondering why do you not, why there wasn't the displacement current on the J on the fourth equation?
Well spotted, Thibault. You get kudos for paying attention. Well done. I didn't write the displacement current because I was focusing on the sub-relativistic limit. And so if you are at velocities that are much smaller than the speed of light, that term is small. Okay, so you don't need it. But if I was worried about relativistic effects, I would have to keep it. So that's the answer.
Okay.
Good question. Thank you.
Thank you for your presentation. It was amazing.
Thank you.
We have another question. I think you already answered this one, but I'll ask them to ask. So Andres asks about the number of CPU hours. I'm not sure if you want
I'm happy to talk
elaborate on that. So
yeah,
Andres, you should have just, if you want to turn on your camera. If not, I'll just ask. Well, they're not responding. So yeah, Andres just asks, I think it's one of the very first simulations you showed. How much time did that simulation take in terms of CPU hours? If I remember, it was one of the.
So this one right here, maybe was the first. I think the simulation is about 2 million CPU hours. I can't read it because the Zoom thing is on top of it. So let me answer maybe that question more generally. So state-of-the-art simulations in plasma are upwards of 1 million CPU hours, always, okay? Now, whether they are 1 million or 20 million or even 100 million actually depends on the types of equations that you're solving. So for example, if you're solving something that looks like the Boltzmann equation, there is, because the dimensionality is higher, you can explore more CPUs, right? So the higher the dimensionality of the problem, or the larger the number of particles you have, the more CPUs you can use. So it's not uncommon these days that kinetic simulations of plasma can take something like 20 million CPU hours for one simulation. Okay. If you're doing MHD like here, your opportunities for using more CPUs are smaller, also because the codes don't scale perfectly, if you know what I mean. So, if you double the size of the problem, that doesn't mean you can use twice as many processors. So there, the simulations tend to use fewer computational hours. But perhaps the most interesting point, right? So this is not just about bragging about how many CPU hours we can use, right? The more interesting point is that even though we're doing these incredibly large simulations, they are still much, much, much smaller than the realistic systems. So, no computer is actually big enough to simulate things that are happening in the solar corona. Okay, so I'll give you, this is best parameterized by using the Reynolds number. The Reynolds number is basically a ratio of, so it's size times velocity divided by viscosity. The Reynolds number in the solar corona can be something like 10 to the 12, okay? The Reynolds number that you can simulate is like 1,000 or maybe 10,000, okay? And that's proportional to the resolution you can have, basically the size of your computer. So we are many orders of magnitude below what we need to actually provide a realistic simulation of anywhere, okay? So that, I think that sets things in context and tells you why exascale is so interesting to us, as is machine learning and maybe quantum computing.
Yeah, I think that's answered it. Being many orders of magnitude below where we need to be is the story of my PhD. So we have another question by, well, two questions actually by Imanj. So I asked that you just ask one of them just so we can give opportunity to someone else. But yeah, I think.
Yeah. Sir, could you explain how exactly does the misalignment of the temperature and pressure density gradients generates a magnetic field?
Yeah, that's a good question. So I just stated that, right? But I didn't explain it. To explain that requires. So the idea was simple. I just said, let there be a temperature gradient and a density gradient that are not aligned, and that somehow magically gives you a battery, right? But I didn't really explain where that comes from. So I'm not sure that I can do justice to that without writing more equations, but the idea is like this. So you see this equation here? I said this was Ohm's law, okay? This is actually not complete. This is a simplification. This Ohm's law, if it were complete, would have another term here on the right-hand side, which would be the electron pressure gradient, a term like this, but for the electrons, okay? Now, you remember maybe that I took the curl of this equation to arrive at the induction equation. When I take the curl of the pressure gradient, this would be the pressure gradient divided by density itself. There's going to be a surviving term that looks like grad n cross grad t. And that term is going to be a source for magnetic field. Now, if you're looking for some intuition, it just has to do with the fact that having a temperature gradient and a density gradient generates currents in my plasma, so electron flows, which then lead to a magnetic field. So that's maybe not the most satisfactory answer, but that's the answer I can give you without writing more equations.
Yes, sir. Thank you, sir. I understand.
Good, thank you.
Great. Thank you. We have another question from Alec. So let me just find you. Oh, here we go. Oh, sorry.
Can you hear me?
Yeah.
So my question is, in the last slides, you mentioned that the Earth's magnetic field was constant in the last billion years.
Roughly.
So, yeah, is it right that the Earth has lost 10% of its magnetic field in the last 150 years? And how come?
So, excellent question, Alec. Thank you. So, when I say the Earth's magnetic field has remained roughly constant, what I mean is, if you look over longish timescales, its magnitude is roughly constant. So of course, it varies, right? And it reverses sometimes, right? And those reversals of the Earth's magnetic field, so, reversal meaning the North Pole becomes the South Pole and vice versa. So those happen, and there's even interesting stories you can tell about how those reversals of the Earth's magnetic field correlate with mini ice ages and things like this. Okay, but the idea is that if you average over these periodic reversals, right, or fluctuations, the amplitude of the field has remained roughly constant. Okay, and the idea is that if there was no induction, if there was no dynamo working, you and I wouldn't be talking, right? The magnetic field would have diffused very quickly, right? Within 10 to the 5 years, the Earth would be left without a magnetic field, and the Earth's magnetic field protected from cosmic radiation, right? And if you were open to that radiation, you wouldn't be here, like I said, nor would I.
Yeah, thank you very much.
Great, and I think we have one last question, so I'll just give them.
Hello.
Yeah. Hi.
So my question was, where exactly at using quantum computing in plasma physics problem, as quantum computing is pretty new, right?
Great question.
So how can we use it in plasma physics?
We can't. Okay. So the short answer, we cannot. Okay. The longer answer is that, people are thinking like this. People are thinking it may take 20 years for there to be a quantum computer that one can use, right? Like one that actually is useful for something, for solving a real problem, right? And it's a mistake to wait 20 years and then start thinking how to use it. Because it's not going to be about taking a code that I have and just porting it to the quantum computer, right? That's not how it's going to work, because it's a fundamentally different architecture. So what people are thinking is, yes, it will take 20 years to get a computer, but it probably will take 20 years for us to understand how we can map our problems into something that can be solved on a quantum computer. Right? So the idea is to have the two lines of thought develop in parallel, so that by the time that there is actually a useful quantum computer, we are ready to use it. Okay, and it's actually a very challenging problem, because, like I said, all our problems are nonlinear. It's not at all obvious how you devise a quantum algorithm that will allow you to solve nonlinear problems. So for example, an example of something I'm playing around with is called the Madelung transformation, which is a transformation you do to the Schrödinger equation that maps it into fluid-like equations. That's very interesting. Okay? It has limitations, but it's very interesting because our MHD equations are similar to those. Okay? So this gives you an idea of the type of mapping that you can do to some problems that might make them easier to solve on a quantum computer. But it's a completely different way of thinking to what we do currently with conventional computing. Like, you don't think like that for conventional computing. So that's the answer.
Thank you.
I think that's also, with that said, I think we can close this session. Thanks again for the very interesting talk. So for the participants listening, I'll just remind you that the competition starts in about 3.5 hours, but in just about 6 hours, our next talk is exactly going to be on quantum computing. We're joined by Tim from NYU Shanghai. So if you're interested in seeing the other side of what the actual computer that might one day help solve these problems may look like, then tune in about 6 hours. So with that said, I'd like to thank our speaker, Professor Nuno Loureiro, once again for joining us, and see you all later. Thank you.
Thank you, Pedro. Thank you, everybody. Good luck.